So we will prove this theorem of Erdős, which says that if you have a R-partite R uniform hypergraph with each, color class has size S, then its extremal number is at most n to the R minus 1 over S to the R minus 1. So which implies that any R-partite R graph has a Turan density 0, as this is little o of n to the little o of n choose R. So we want to prove this. We use induction on R. If R is 2, then this is nothing but the extremal number of KSS. And in undergraduate graph theory, we learned that this is actually smaller than n to the 2 minus 1 over S. So assume R is at least 3, and we already know that the extremal number of n k R minus 1 uniform hypergraph with each set, each color class has size S is at most n to the R minus 1 minus 1 over S to the R minus 2. So let H be an R uniform hypergraph with more than n to the R minus 1 over S to the R minus 1 edges. And we want to just prove that this H contains a copy of this complete R-partite. This complete R-partite R uniform hypergraph. Say, and let V be the vertex of V. So how we will do it is we want to reduce the problem onto R minus 1 uniform hypergraph somehow. For that, we consider so there are R vertices in each edge. Now, how we will consider it is that we will consider the incidence relation between vertex and this edge. So in other words, we consider let's not put it as an incidence relation. We have a R vertex in each edge. And we consider one vertex of it and R minus 1 vertex of it, and then we consider the relationship between these two. For that, we consider a graph representing such relation, which is bipartite graph G with bipartition A union B, where A represents the set of vertices and B is collection of R minus 1 sets in V. And where we have an edge in G, where A is in A and B is in B, if and only if A union B is in the original hypergraph. So for example, if we have a hypergraph H 1, 2, 3, 4, say 2, 3, 4, then you have 1, 2, 3, 4, and you have 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. Then 1 and 2, 3 forms an edge, so we add an edge. 2 and 1, 3 forms an edge. 3 and 1, 2 forms an edge. 4 and 2, 3. 3 and 2, 4, 2, 4. 2 and 3, 4 forms an edge, because this. So each edge here, each R, edge of size R, hyperedge, give us R edges in this graph G. Then we know that if you take the degree sum of the vertices in A, then this counts every hyperedge exactly r times. So we know that this is r bigger than r times n to the r minus 1 over s to the r minus 1. This is actually r times number of edges in H. So this is what we have. But again, similar to the previous, bipartite case, we consider, this is sum of the degree, and we consider the sum of the, other functions of degree. So before, when we do K4, we consider, this function and we sum it up, and then it has some meaning, and we interpret the meaning in combinatorial way. Similarly, we do this. For each B, here, we consider the degree of B, and we raise up the power by S. Then so as before, this f of x is x to the s is a convex function with s being x being natural number. So by the convexity, we again have this inequality, just like before. And this is again, so summation of all degree of B is same as the summation of all degrees in A in bipartite graph. So this is again at least as big as this. So you plug that in, then r times n to the r minus 1 over s to the r minus 1 over B. B has size n to the r minus 1. So we have this. So roughly, this lower part is n to the r minus 1. And then this part is also n to the r minus 1, roughly, times some constant. And then we have this. So if you compute, then this is roughly n to the r minus 1 times plus, say, s minus 1 over s to the r minus 2. Because n to the r minus 1 over s to the r minus 1 minus r plus 1 is this inside. So you get this, and you multiply by s, then this. And then b itself is roughly n to the r minus 1. So this is the upper bound. And you also have to come up with the constant, but you can actually show that it's at least twice times this. But what's the meaning of this? This counts as tuples of neighbors over vertex B in here. So meaning that you have a vertex B and then you have neighbor MV. Then you count all the tuple in here. So we have that the summation of degree of B to the S is same as you consider all the vertex B1 to be S in A sorry, not A, B. No, sorry. Let's just write A such that you take a common neighborhood of this Pi and we add a number. What does this mean is that so this is what we count in this expression. But for each x1 to xs, this tuple, how many times does it count? Is it counted? So we have B, which have, say, x1 to xs, and another B prime, which also have this. In that case, this specific tuple might be counted twice. The number of times it is counted is that you take x1 to xs, this tuple, some of them might be the same vertex, and then consider the common neighborhood of this. And for each, this B has a neighbor which contains all s of them, so it counts this specific tuple. And all of this counts that, and then all of that outside does not count this tuple. So this counts exactly how many times each tuple gets counted. So we have this equality. And then this is that when all the vertices are different, so we can divide into two. All the vertices are different, and all the vertices are not distinct. So we can analyze these two terms on how large it is. So if there exists P1 to Ps, let's consider the first case, which are distinct. With this common neighborhood size bigger than n to the r minus 1 over s to the r minus 2. Then what we do is we consider an r minus 1 graph, say h prime, with E h prime is consider all the sets of size r minus 1 which lies in this. So common neighbor of this G. So remember, so on this B part, these are the vertices of G. But these are also sets of size r minus 1 inside of B. So that's also correspond to the sets of size r minus 1. So it forms an R uniform hypergraph. Then this is an R minus 1 uniform hypergraph with how many edges? More than this many edges. So then induction hypothesis is a copy of k to the R minus 1 s to the s in H prime. So let's say R is 3, then you get R is 3 and S is 2. Then you get a K2 in H prime. And you have this two vertex V1 and V2, where H prime is obtained from these two. Then what does this mean? So by the definition of this S prime, these four sets of size 2 are all in common neighbor of these two vertices in G, meaning that the V1 plus this edge together, these three vertices forms a hyperedge in H. And this V2 with the same edge, these three vertices also forms an hyperedge in H. That apply to all these three, this three, and this. So this copy, in the same logic, this copy with V1 and V2 forms a copy of K to the R uniform R type complete hypergraph in the original hypergraph. H. Hence, this first term, each of these is actually bounded by this number. So let's say this is star. Then star is at most. So the number of such pair is at most, and such tuple is at most n to the s, and each of them give us this number. And the second term is, so you want to count the number of all tuples which has repetitions. So we can write this as this. So how do you do it? We just want a upper bound on the number of such terms. So you choose that you choose I and j from 1 to s, which are different. And then we want to make the vi and vj same. So choosing this, there are s square ways. And then once you choose this, and then you take v1, v2, and vs in an n way. But whenever you choose a vi, then you just keep vj, choice of vj, and you just give the same choice to vj. So s squared times n to the s minus 1 is the upper bound on the number of ways to choose this tuple. So this part is s squared times n to the s minus 1. And each of the time that we add, this term has size and more size of b, which is n choose r minus 1. So this all together is at most 2 times n to the r plus s minus 1 minus 1 over s to the r minus 2. I mean, this binary inequality is true as, I mean, n is bigger than s to the 4 and s is at least 2. So now we have this, and we have before proved this bound. So we have this lower bound with actually, so this is a strict inequality. So this is lower bound, and we have the same number here as an upper bound. So this is a contradiction. So this proves the theorem. So we have proved this, that any R uniform, R partite hypergraph, the Turan density is 0, and moreover, I mean, it has, we can find the upper bound on the extremal number of this hypergraph. And in next video, we will prove some other, I mean, theorem regarding supersaturation, and then we will combine supersaturation result with this hypergraph result to prove some other results about the graph.